So let's just focus a little bit on the Earth and the Sun system. The Sun is actually just one of billions of stars, and we'll talk more about that later, but it's just kind of a typical star. And here we have a beautiful photograph of, this is the ISS, International Space Station, as it orbits the Earth, and here it is coming up upon our Sun. You can kind of see the Earth in there. That is so beautiful. So the Earth and the other planets are held in orbit about the Sun, just as other planets are held in orbit about their star due to the force of gravity. Let's see if I can remember what this is. The force of gravity, we take the gravitational constant times the masses of both objects. This would be the mass of the planet, the mass of the Earth, and the mass of the Sun, and we divide by the distance between them, and we square that. So the force of gravity that the Earth feels is different than the force of gravity that other planets feel due to their different masses and their different radii. So here we have our Sun not drawn to scale and the Earth orbiting the Sun. So here is the Sun and here is the Earth orbiting the Sun. Now, one of the things I emphasize in this class is it's all about counterclockwise. Counterclockwise, when it comes to our solar system anyway. If it's not going counterclockwise, it's going backwards, which some things do go backwards. I think I mentioned that Venus actually spins on its axis backwards. If I was going to go, you can kind of see these axis of rotation for the Earth. Now you see how the axis of rotation are kind of all pointed in the same direction. We'll talk about that in a minute. But the Earth orbits the Sun and it spins on its axis. It spins on its axis counterclockwise too. Okay. Now you see where the Earth actually the Earth's orbit lies in a plane about the Sun, and if I were to draw the other planets that we talked about in part 2, of course I would have Mercury, and then Venus and Earth and Mars and Jupiter and Saturn, etc. And that actually, they orbit the Sun in what's called a plane of the ecliptic. And that's kind of an important term. Plane of the ecliptic. So as the Earth orbits the Sun, on the previous slide it says how long does it take the Earth to go around the Sun once? Well, a year, and that's 365.25 days. And the Earth spins on its axis once every 24 hours. Actually, I think it's kind of an interesting sidebar. The Earth hasn't always rotated. The days weren't always 24 hours long. They used to be much shorter, and actually the rotation is slowing down a little bit, so they're getting longer. But as the Earth spins on its axis, when it spins towards the Sun, we have daytime, and when it spins away from the Sun, we have nighttime. So I bet you're probably pretty good with that. On the previous figure, you saw the tilted axis of rotation, and here we have the tilted axis of rotation. If you buy a decent globe, they will have the axis of rotation tilted like that. It's not because it's broken, it's because it's just trying to represent the real deal. Now, it's tilted in a matter of saying in what we say 23.5 degrees. It's 23.5 degrees from if it were straight up and down. So here's my axis straight up and down, perpendicular to what? How it orbits the Sun, the plane of the ecliptic, but it is tilted 23.5 degrees from that, being perpendicular. So that's how that works. Cool. And I don't know if where I mentioned it, but the tilt we think was caused by actually early on, and it could have been caused, I think I read, at the same time that the moon was caused. Basically, the Earth got hit early on in its formation by something the size of Mars, and basically tilted it and maybe created the moon out of that. Okay. So one of the things that's hard to relay, I think, in the videos like this instead of like in person, is that as the Earth goes around the Sun, orbits the Sun in the course of a year, its axis of rotation, like you saw a little bit ago on the previous figure, its axis of rotation is always pointed in the same direction. Okay? It's kind of like a dancer that always has kind of the faces one direction, I think, something like that. Well, that direction, if you go far enough, or that direction, that apparent direction, is always to a star. The north axis of rotation, anyway, right now is to the star called Polaris. So it's kind of cool, and this has consequences because throughout the course of the night, we're going to talk about how stars kind of tend to kind of rotate in a circle. They stay in a pattern we call constellations, but they go, I think it must be counterclockwise. They go counterclockwise around Polaris. Okay, so yeah. I have a video coming up that hopefully will kind of shed a little bit more light on this, but if we know that we have seasons as the Earth orbits the sun. So of course we have summer, okay, and then after summer we have fall. After fall we have winter, okay, and after winter we have spring. So that happens throughout the course of 365 1/4 days. But now, why is that? And actually, if the Earth's axis of rotation were not tilted, I like this figure because we see the North Pole tilted, the axis of rotation tilted. Okay, if it were not tilted, we would have no seasons. If it were not tilted, I guarantee you, it would just be very hot at the equator and very cold at both poles, and in between you'd have the same, you wouldn't experience seasons. I'll try to kind of convince you of that. We call these important times when the sun is directly pointed toward when the Earth's north axis of rotation is directly pointed towards the sun, or I should say not directly, leaned as much in towards the sun as possible in the northern hemisphere, we are experiencing summer. Then we go 3 months later, and here we are kind of at a sideways, our tilt is sideways relative to the sun, and that's one of our equinoxes. That's the autumnal equinox. And then 3 months later, here we are in winter, and we are at a solstice, where the northern hemisphere, the northern axis of rotation is tilted away from the sun, and that actually is our winter solstice. And then 3 months later, here we are around a spring, and that's another one of our equinoxes called the vernal equinox. And then 3 months later, here we are back to summer, and we have two solstices. We have the summer solstice and the winter solstice. And those are the extremes when the Earth's axis of rotation is pointed leaning towards or leaning away because of its tilted axis of rotation. So now, when the axis of rotation, when it changes as the Earth orbits the sun, we get a number of things change. One is that we get a different number of daylight hours. So in the summer, of course, we have maximum daylight hours at the summer solstice, and we have maximum daylight hours, and the sun's rays are most direct. I hope they kind of show you. You can see that on the video that I brought up. And the winter solstice, then we have the shortest days, and the sun's rays are least direct in the northern hemisphere. And so between our two solstices, between our two extremes, we have equinoxes. So here's our solstice, and here are our equinoxes. We have an equinox in fall, an autumnal equinox, and then we have an equinox in spring, a vernal equinox. And no, I don't think that you can stand a room upright without it falling. I don't know. There's certain kind of, I think, sort of silly things that people talk about. The equinox, when the Earth's axis of rotation is kind of, it's kind of edge on relative to the sun. But what is equal is that we have equal hours of daylight and equal hours of nighttime on those days. So I think I've kind of come full circle, no pun intended. So I hope you enjoy the video I picked for this one.